let me welcome you to this lecture. We have now established that the complete list of symmetry operations present within a given molecule uh, follows all the rules or criteria of a mathematical group, and therefore it constitutes a mathematical group. Also, we have seen that the symmetry operations, which are conjugates of each other, they form smaller subgroups within a given group, and we call these subgroups as class. And we can find out the symmetry operations within a given class by using a mathematical operation that is known as similarity transformation. Now, uh, different molecules have different symmetry elements, and that is why the list of symmetry operations within different molecules are different, and the collection and these different collection of symmetry operations in molecules form certain mathematical groups, and that is why we need to distinct these mathematical groups formed by different collection of symmetry operations. So during this lecture we will learn what kind of mathematical groups are formed by different collection of symmetry operations. And the first thing that we should learn is that the notation that we use to designate or denote these mathematical groups formed by symmetry operations is known as Symmetry's notation, or we also call them as point group symbols. And the mathematical groups that are formed by symmetry operations within a given molecule are is known as actually a point group, because we consider the atoms to be points while visualizing or identifying the elements of symmetry that are present within a given molecule. That is why we call it a point group, the group that is formed by the collection of symmetry operation within a given molecule. And the symbols that we use to denote these point groups are essentially called either point group symbols or as Symmetry's notation. Now, we will begin this exercise to find out the kind of point groups that are formed by different class of symmetry or different collection of symmetry operations by starting with molecules where there is only one type of element of symmetry is present. So let us begin this with molecules where there is no other symmetry operation apart from the identity element, and we know that the identity element produces only one symmetry operation, that is the identity operation itself. And the point group, when only identity element is present, is known as the C1 point group. So then let us look at the point group or the mathematical group that is formed when only a plane of symmetry is present within a molecule. That is, if only a sigma is present, a plane of symmetry is the only element of symmetry. We know a plane of symmetry generates two symmetry operation, that is a reflection operation, and sigma squared is equal to identity, and that is why only two operations are generated by this plane of symmetry. And the group that is formed will be of order 2 because there are only two elements within this group, and we call this group as CS point group. Now you can also have molecules where only a center of symmetry is present as the only symmetry element, and in this case also the center of symmetry produces only two operations, that is the inversion operation and the identity operation, which is I squared, and therefore this is also going to form a group of order 2, as only two symmetry operations are there, and the group is designated as Ci point group now. Now let us look at groups that are formed when only a proper axis of symmetry is present within a molecule. So let us say only a Cn axis of symmetry, that is a proper axis of symmetry of order n, is present within a given molecule. Now, unlike plane of symmetry or center of symmetry, a proper axis of symmetry may produce more than two symmetry operations depending upon the value of n, because we know the Cn axis of symmetry can produce Cn1, Cn2, and we can go on until Cnn minus 1, and then Cnn is equal to identity. So total 1 to n, there are total of n symmetry operations are generated by this proper axis of symmetry. So the group formed by symmetry operations generated by a proper axis of symmetry will be of order n, as n symmetry operations are there total. And such a group is designated as, or the notation for such a group is going to be Cn, point group symbol is going to be Cn. We call it the Cn point group. So one more thing to remember about such point groups where only a proper axis of, or which is formed by only symmetry operations generated by a proper axis of symmetry, is that such groups are going to be cyclic in nature, as the only one element and its different degrees are the elements of the group, and such groups are therefore going to be cyclic groups. And also we have learned that cyclic groups are abelian in nature, that is multiplication of the elements within this group are going to follow the commutative law of multiplication, and that is why they are going to be also abelian in nature. So we will now move on to see the mathematical groups or point groups formed when a improper axis of symmetry is the only symmetry element that is present within a given molecule. And in this case, when an improper axis of symmetry is present, that is Sn axis of symmetry is present, the number of symmetry operations generated by an Sn axis of symmetry, improper axis of symmetry, vary depending upon the value of n, that is again whether it is n is an odd number or n is an even number. The number of symmetry operations generated by Sn can be different, because when n is even, we can have symmetry operations like Sn1, Sn2, Sn3, and we can go on until Sn, which is Cn n and sigma n. And since n is a even number, sigma to the power n is going to be equal to identity. Cn n is also going to be identity, so this is equal to identity. So total, we will have n symmetry operations are generated by a improper axis of symmetry, and the order of the group is going to be equal to n in this case. So we have also, what we will notice here, Cn2 sigma 2 is when we simplify Sn2, we will get this, and sigma 2 is going to be identity, so it is Cn2, which is actually 2 times 2 pi by n degree rotation, or we can say this is actually equal to Cn by 2 1. we do so, because now n is divisible by 2 as n is an even number, this is as good as doing Cn by 2 rotation one time, and therefore whenever we have a even order improper axis of symmetry is present within a molecule, there is going to be a proper axis of symmetry as well that will coexist with the improper axis of symmetry, and which is going to be collinear with the improper axis of symmetry, and that improper axis of symmetry is going to be Cn by 2 improper axis of symmetry. Oh, sorry, proper axis of symmetry. And all the symmetry operations that are generated by a Cn by 2 axis of symmetry will be available when you simplify the symmetry operations that are generated by the improper axis of symmetry. So that is going to coexist, but in this case we must note, when we have a proper axis of symmetry of even order, then the point group, that is symbol that we are going to use, is going to be Sn point group, not Cn by 2 point group, even though Cn by 2 is going to be present within the molecule. We will designate the point group as Sn point group. This is not the case when we have an improper axis of symmetry of odd order. So when n is odd, the situation is entirely different, as we don't have now n symmetry operations, but 2n symmetry operations are generated by an improper axis of symmetry of odd order, that is Sn1, Sn2. It will go on until Sn will be equal to Cn and sigma n. Since n is odd number, sigma n is going to be, Cnn is going to be identity, sigma n is going to be equal to sigma. So Sn is essentially equal to sigma. Now you can go on until Sn2n, where you will find which is equal to actually identity. So total number of symmetry operations that are generated by Sn axis of odd order is equal to 2n, and the order of this mathematical group, the number of elements within this mathematical group, is going to be equal to 2n. Also, what we should note is this is going to be Cn2 sigma 2. So this is equal to Cn2. Now n is not divisible by 2, so we cannot write Cn by 2 in this case, and that is why what we have here is actually a symmetry operation that is generated by a Cn axis of symmetry. Also, at the same time, if you simplify all the symmetry operations generated by an Sn axis of symmetry of odd order, you will find all symmetry operations that are generated by a Cn axis of symmetry. So what it means is that whenever we have an improper axis of symmetry of odd order, a proper axis of symmetry, that is Cn, will also coexist along with the improper axis of symmetry, and both of these two symmetry axes are going to be collinear with each other. Apart from this Cn, another symmetry element is going to coexist when you have an Sn axis of symmetry of odd order, that is a sigma is going to be, because sigma also will exist independently apart from the Cn axis of symmetry. So also one more thing to remember, or here or observe here, is that this sigma is actually perpendicular to the Sn axis of symmetry, and since Cn and Sn both are collinear with each other, this sigma is also, this plane of symmetry is also perpendicular to the Cn axis of symmetry. So we can designate this sigma as sigma h or sigma horizontal. So we designate all the planes which are perpendicular to the proper axis of symmetry of highest order as sigma h. We should remember that. So we will designate this particular plane of symmetry as sigma h, and the point group now, unlike when we have improper axis of symmetry of even order, the point group will not be Sn in this case. Instead of point group, we will call it as CNH point group, because we have Cn as well as we have a sigma h in this case. We will designate the point group as CNH, not as SNH, and the order of this point group is 2n. Already we have seen that. So this is different from what we see in case of improper axis of symmetry of even order. So the point groups that we get from the symmetry operations that are generated by even order or in odd order improper axis of symmetry are entirely different. So now we are done with the point groups that are formed when only one type of element of symmetry is present within a given molecule, and now we should go and see what kind of point groups are formed when we have more than one type of element of symmetry within a given molecule. So before we do this, we must categorize or classify the molecules into two different categories or kinds. That is, the first type of molecules have multiple proper axis of symmetry of order higher than 2. So we have more than one type of more than one proper axis of symmetry of order higher than 2, that is C2. So if we have more than one C3, C4, C5 or C6 axis of symmetry within a molecule, we would say the molecule will belong to the first class of, actually, or first type of category of molecules. And examples of such molecules we have already seen. So for example, in case of tetrahedral molecule, we have seen that there are 4 C3 axes of symmetry, and there are 4 C3 axes of symmetry we have seen in tetrahedral molecules. Similarly, we have seen that there are 3 C4 axes of symmetry in octahedral molecules. So such molecules which are highly symmetric in nature and contain more than one proper axis of symmetry of higher order, or that is higher than 2, will belong to this category. And the point group symbols are very special point group symbols in these cases. So for tetrahedral, the point group symbol, that there are 24 symmetry operations within a tetrahedral, and these 24 symmetry operations together form a mathematical group which we designate as TD point group. Similarly, the 48 symmetry operations that are present within an octahedron, we designate the point group as OH point group this time. So these are different types of highly symmetric molecular point groups. We also have, say, for example, icosahedron is also there, which contains multiple proper axes of symmetry of order higher than 2, and there are so on. There are several other types of highly symmetric systems. So the second class of molecules, or second category of molecules that we are going to discuss, and majority of real life molecules fall into this category, the second category, which contains only one proper axis of symmetry of order higher than 2. So this is the second category of molecules that we are going to discuss, and what we are going to see is how the combination of different symmetry of elements with proper axis of symmetry of order higher than 2 forms different kinds of molecular point groups in this case. So to begin with, one very important observation that we should learn is that if you find by observation one C2 axis of symmetry perpendicular to a proper axis of symmetry Cn, then there is definitely total n C2 axes which are perpendicular to the Cn axis of symmetry. That means if you have one C2 which is perpendicular to the Cn, if you find one, or if only one, if you somehow find, then there must be total n C2s are going to be there. This is a necessary condition put by group theory, and we will see how it is possible. Or one example we should see first, where just to verify this observation is that, say, in case of the BF3 molecule, which is trigonal planar in nature, so if we assume that all the atoms of BF3 molecule lie on this plane of the board, then the C3 axis of symmetry will pass through the boron atom, while there are three C2 axis of symmetry which passes through the 3pf bonds here, you see. So there are three C2 axes perpendicular to the C3 axis. As we have said, there is going to be n C2 if you find one C2 perpendicular to the Cn axis of symmetry, and this is the case in case of the BF3 molecule. We will try to verify this observation again by using a slightly mathematical procedure. So let us assume a molecule, or consider a molecule with C4 axis of symmetry and only one C2 axis of symmetry perpendicular to that C4 axis of symmetry. And let us take the Cartesian coordinate system as the reference here again. This is x-axis, this is z, and this is y-axis. And the principal axis we will always take along the z-axis. So C4 axis, that is the proper axis of symmetry of highest order, we call it the principal axis, is along the z-axis, while the C2 axis that we assumed is perpendicular to the C4 axis of symmetry passes through the, or goes, or is along the x-axis here. So if you consider an atom or a point with coordinate x, y, z, and then do the operation C2 x first on this point, what you will find is that you have to rotate it along the C2 axis of symmetry, which is along the x-axis of symmetry, x-axis, by 180 degree. And if you do so, y will go to now minus y, and z-axis will go to minus z, that you can see, but x will not change. X coordinate is not going to change if you are going to rotate along the x-axis, and that is why x will remain x, y goes to minus y upon rotation of 180 degree, z as well goes to minus z. Now the C4 axis of symmetry, it produces three elements of symmetry operations, that is C41, C42 and C43. C44 is going to be identity. So if we do C41 now on this, on the coordinate that we get after doing C2, then you have to rotate again along the z-axis by 90 degree for C41 operation, and x coordinate will reach y, you can see. So x becomes y after doing C4, and minus y will go to x, because if you rotate in this direction, minus y will come to x, x will come to y. So minus y becomes plus x, and minus z, as you see, since we are rotating with respect to the C4, that is the z-axis, does not change, and minus z coordinate remains minus z. So this is the final coordinates that we get after doing C2 as well as C41 on x, y, z coordinate here. So it means that what we have done is we have done both C41 and C2. So C41, this is one. So this will give us essentially, after doing this, what we are doing is carrying out the combination of both the symmetry operations on this initial coordinate over here, and the result of this product of these two symmetry operations must be an element of the group itself if it has to form a mathematical group. So this result should be an element or say a symmetry operation that has to be present within this system. And if we assume now a C2 axis of symmetry, say let's designate it as C2xy, because this C2 axis of symmetry we assume it to bisect the x and the angle formed by x and y axis, as well as it is on the xy plane, so that it is perpendicular to the C4 axis of symmetry. So if we assume this C2 axis, and then if we do a C2 rotation with respect to this particular C2 axis of symmetry, then x will come to y, y will go to x, and z will go to minus z. So if we do on the initial coordinates this C2 xy, but you will find x goes to y, y goes to x, but z goes to minus z. So we get directly these coordinates by performing C2xy. So that means the combination of C2x and C4 is equal to C2xy, and C2xy must be present within the same group. So otherwise, the combination of these two symmetry operations will not be an element of the group. And now let us proceed further and then do C42 operations. That the coordinate over here is going to change, which is going to be, that is 180 degree rotation with respect to z axis. Then x goes to minus x, minus y after 180 degree rotation will come to plus y, and minus z will not change, that is going to be this one. And if you notice carefully, if you have a C2, if you consider a C2 axis of symmetry along the y-axis, then you will find you can come directly from this initial coordinate to this final coordinate by doing C2y operation. So that means the combination of C2 and C42 is equal to C2y. Similarly, if we do the C43 operation over here, the coordinates this time is going to be, we have to rotate by 270 degree. So x will go to minus y will come to minus x, and z will not change, it is going to remain as minus z. So this is the coordinate, and if you assume is an axis which passes through the origin and bisects the angle between minus x and y axis over here, then y goes to minus x, x goes to minus y upon doing 180 degree rotation with respect to this particular axis. X goes to minus y, x comes minus y, y goes to minus x, and z goes to minus z. So this is C2 minus xy axis actually. If we do that's what we get. So C43 will be equal to C2 minus xy. So this is what we have seen over here. We assume the molecule has only one C4 axis of symmetry and one C2 axis of symmetry perpendicular to the C4 axis of symmetry. But what we found is a combination of all the symmetry operations that are generated by these two symmetry elements, that is the C4 axis and the C2 axis along the x-axis, produces such symmetry operations, or necessitates that these three C2 axes must be there within the these two symmetry operations generated by these three C2 axes must be present within the group, or otherwise it will not constitute a mathematical group, as the product will not be part of a group. So that is why it is a it is a must that these three symmetry operations, these three C2 axes of symmetry are also present along with the C2 axis, that is along the x-axis. So total there must be 4 C2 axes along perpendicular to the C4 axis of symmetry. So again we have proved that there are n C2 axes perpendicular to the Cn. So if you find one C2 axis, there will be n C2 axis perpendicular to the Cn axis of symmetry. So this is a condition set by the principles of group theory, and we cannot deviate from this particular condition. So this brings us to the end of this lecture. We will discuss more about the point groups that are formed by combination of different symmetry elements during the next lecture. So till then, I thank you very much for being with me during this